Hi everybody. So in this last video on the periodic trends, I'm just going to talk about a couple more additional trends that are predictable using quantum mechanics and electron configuration. The first trend I want to talk about here is the trend in reactivity of group 1a and group 7a elements. Okay, so with group 1a and group 7a, or with metals and nonmetals, we often have these type of reactions here, which is a reaction where metal reacts with a nonmetal. So the reaction, for example, could be sodium reacting with sulfur producing sodium sulfite, or lithium reacting with nitrogen gas to produce lithium nitride. You can have sodium and chloride reacting, chlorine gas in this case, then you produce sodium chloride as a result. Okay, if you look at this reaction, it's a redox reaction. How do I know it's a redox reaction? Because the oxidation number, if you look carefully, of sodium is 0 in the reactant and it's +1 in the product. Similarly, for the sulfur, the oxidation number is 0, but then it becomes -2 in the product. So I know there's a change in oxidation number, and as a result I know it's a redox reaction. The metal here, because it's oxidized, act as a reducing agent. Vice versa, the nonmetal, because it's reduced, acts as an oxidizing agent. So the question that we want to ask as far as trends are concerned in this particular topic is to ask, is there a trend in the strength of reducing power for metals? For example, if I want to compare how strong sodium versus lithium is, because they're in the same group, I want to know how strong one is compared to the other one with respect to their reducing power. Can I make that prediction based on electron configuration? And similarly, I want to make that same prediction with the nonmetals, specifically for the group 7a or the halogens. And I'm going to go through the reasoning here for the group 1a, and hopefully from there you can then work on your own to determine what the trend would be for the nonmetals. So for the metals, if you think about it, in this reaction, what happens is the metals, in this case the alkali metals, they're going to form the cation form. They're going from 0 to +1 in this case. So they're losing an electron. Okay, so the question, if we want to ask if there's a trend, is to ask how easy is for that metal to lose that electron as we go top to bottom in the periodic table. Okay, and to answer that question, you really need to look at the electron configuration of all these metals. If you look here, you notice that lithium is this configuration, sodium is this, and potassium is this. And of course, they all have 1 electrons to lose. And what you notice, though, of course, is that potassium, the electron is located in 4s, sodium is 3s, and lithium is 2s. What's the difference there? The difference is that with potassium, that 1 electron is located the furthest away from the nucleus in comparison to sodium and lithium. Why is that important? That's important because in the reaction that we're discussing, it's the reaction where the metal converts to the cation form. So the loss of that 1 electron is very important. And with this potassium having the electron all the way in the 4th shell, it's going to be a lot easier for potassium to lose that electron, energetically the easiest to lose that electron compared to either sodium or lithium. Lithium would be the hardest because that electron is located the closest to the nucleus. Why is that important? That's important because in the reaction we're measuring how easy it is for these metal to lose that electron. The easier the metal loses the electron, the stronger its reducing power is. Okay, so in this case then I would make the prediction that potassium has the strongest reducing power, followed by sodium, followed by lithium, because of the ease of the loss of these electrons. And of course that has been shown to be correct experimentally, that prediction. Now what I want you to do is use the same reasoning, same kind of thought process that I just used for the group 1a to explain the oxidizing power trend for the halogens, fluorine, chlorine, bromine, and iodine, based on their electron configuration. So again, what you want to do is think about what does oxidizing agent mean? What do I mean by oxidizing agent strength? And what process am I looking at, which is this reaction right here? And how should I interpret the electron configuration in light of this reaction for the nonmetal? Okay? So the last trend I want to talk about is a trend that relates to something referred to as the isoelectronic series. An isoelectronic series is basically an atom or a bunch of ions that all have the same number of electrons but different number of protons. Okay? The word iso in chemistry always means the same, whether same structure like isomer, or in this case isoelectronic just means the same electron, same number of electrons in this case. Now, what is an example of an isoelectronic series? Right here is an example of them. S2 minus, Cl minus, Ar, K plus, and Ca2 plus. Okay? All these atoms have the following electronic configuration, which is, neon and then 3s2 and 3p6. In other words, they all have the same number of electrons as argon, which is 18 electrons. Okay? You can count this if you don't believe me. 3s2, 3p4, of course, for sulfite, which is 16 electrons. But because it's S2 minus, you add 2 more electrons, becomes 18 electrons, becomes like this, right? Cl is 17 electrons plus 1 from the Cl minus becomes 18, same like argon. Argon, of course, is already 18. K is 19 electron, but K plus is 18 electron because it lost that 1 electron. Calcium itself, the atom is 20 electrons, but then calcium 2 plus lost 2 electrons, so then it becomes 18 electrons as well. The question that we wanted to answer here is, can we make prediction on size of these isoelectronic series of species, based on their electron configuration? And the answer is we can, and actually very easily, because they all have the same number of electrons. That means that we don't really need to think about the electrons so much as we need to think about the atomic number, which is Z. So what we really need to do when we're trying to predict size in this case is to look at the Z compared to the number of electrons. If there's a lot of, if the Z is large, in other words, there's a lot of protons, you're going to expect a smaller size because the attraction between the proton and the electrons will be stronger, and as a result, the size would be smaller. Whereas if there is a smaller value of Z or fewer number of protons, relatively speaking, then you're going to expect a larger size because there's a weaker attraction between the proton and the electrons. And in fact, that's what we see here when we look at this isoelectronic series that I just talked about. You notice that sulfite has the largest size, and then calcium has the smallest size. And of course, the reason for that is because sulfite has only 16 protons, right? And calcium has 20 protons, even though they all have the same number of electrons. So this one has the strongest attraction between the nucleus and its electrons, so as a result, smallest size. Vice versa, this one has the weakest attraction, so therefore the largest size. You actually see this pattern again and again in the periodic table. That's why it's called a trend. So it's trend in ionic radii in this case. If you look, for example, here, nitrite, all the way to aluminum ion, they are all isoelectronic, these guys, okay? And you can see that it goes largest, smaller, and smallest right here. And then in fact you can go with Si4 plus as well, being even smaller than that one, okay? And then the pattern repeats itself with phosphorus, P3 minus, big, smaller, all the way to this one being the smallest one. Pattern repeats again here. Okay, so what I want you to do is again kind of understand this, explain it using the concept of electron configuration and atomic number, and this will be useful for us when we talked about ionic bonding in the next topic. Okay, so this is the end of this topic on quantum mechanics. We spent quite a bit of time talking about how quantum mechanics came about, the different components of quantum mechanics, and how we can use it to predict periodic trends and explain them. There's a lot other things that you can do with quantum mechanics, but without the necessary, mathematical abilities, it would be hard for us to implement that in this class. But we really have learned quite a bit about the power of quantum mechanics, and I hope that you're able to use what we learned here to make some other predictions on properties of elements.